Hey everyone, welcome to video 3 of this series. In this video, we're going to be covering an introduction to the Grasshopper interface inside of Rhino and go over some introductory basics as well as some introductions to programmatic ways of thinking inside of Grasshopper. Like in the previous 2 videos, we're going to open up our Rhino environment. Once you have Rhino open, there's 2 ways that you can go ahead and access Grasshopper. So the first way is going to be to just type into our command line interface here. We can type the word Grasshopper, and this is going to pull up our Grasshopper window. Additionally, we can go to the Launch Grasshopper option or icon in the upper tabs for Rhino. So typically I just am going to type in Grasshopper, it's going to autofill for me, and then we can hit enter. And this is going to load our Grasshopper window. Once we see that Grasshopper loads, we can see that this is a kind of free-floating window that occurs in front of our Rhino interface. One important thing to note is that if we made our Grasshopper window full screen in this instance, we no longer see what's happening in Rhino. Since both Rhino and Grasshopper are kind of partners when we're working with them, we want to be able to visualize what's going on in each screen. So if you have 2 screens, then fantastic, put one window on one and the other on the other screen. If you don't, it's totally fine. We're going to just be using one screen here, but what I recommend is just kind of docking one to be about half of the screen, and then double clicking into one particular perspective or viewport. So we can double click in there like in previous videos. Now we have that viewport active in Rhino behind our Grasshopper window. So inside of this Grasshopper window, we get a kind of quick option for previously loaded files or recent files that we can click into if we have those and want to reopen them. If we don't, it says at the top here a few options to get us started, which it mentions either drag a new component onto the canvas, so we can drag what will be called components, and we'll discuss later on in this video, into the canvas to go ahead and get our file started. Alternatively, we can double click the canvas to create a new component. So these components are going to be our kind of primary interface or thing to act with inside of the Grasshopper interface. So that's another way that we could get a file started, or open an existing document via the menu or tiles. So what it's mentioning there is to go to just File, and we could open a document here. Alternatively, if we don't have a document to open, we can just go ahead and click on New Document. Once we click on New Document, those recent files are going to fade away, and we just see this kind of gray space here where we can use our scroll wheel to zoom in and out. We can use our right button on our mouse to pan around the scene, but this is essentially a 2D scene, which is not meant to actually visualize the 3D information that's going to be occurring inside of our Rhino environment. So our Rhino environment is still going to be the environment in which we display our 3D geometry. What this Grasshopper window is for is a visual node-based programming environment, basically connecting certain data embedded into what are called components to make representations of the geometry, which we can preview inside of the Rhino environment. So basically, this is just going to be our 2D coding interface where we'll build up a series of components that communicate with each other through what are called nodes, and we'll have these kind of visualized wires that show the path of each node or component into one another. When we're building something inside of Rhino, I'll just click into my Rhino screen just to activate that, but we can still keep both windows up and visualized. So if I click into Rhino and I type in the command line, let's say sphere, and then hit enter, it's going to prompt me for additional information. So we covered this in the first video a little bit, but right now it's asking for the center of the sphere. So a point that locates the center of the sphere. So I can left click to deposit that point. It's then additionally going to ask for a radius input parameter. So we have to define some given radius. So let's say we want this radius to be 12. We can type 12, input that parameter into the command, hit enter, and if we go into shaded view here, we can now see that that 12 radius sphere is located centrally around the point that we placed in space. So Grasshopper is going to be fairly similar in that we have certain components that make geometry, and what they require is input parameters to define certain properties of that geometry, just like we just did inside of Rhino. So if we go ahead and delete that sphere, we can go into our Grasshopper window, and if we want to construct a sphere inside of Grasshopper, just like where Rhino, we would type into the command line a command, and then we get access to several suggestions related to whatever that command is that we're typing. In Grasshopper, we can double click on our canvas and begin typing whatever that command may be. So in this case, if we want to construct a sphere, we can type sphere. We can see that there's an option now here that it's suggesting, which is called sphere, and it has a small sphere icon to the left of it. If we hover over that, it gives us additional information saying create a spherical surface. If we click on that, it's going to instantiate or add a component, which is this little battery thing in our canvas. Now, in our Rhino interface, we actually see in that window that some geometry has instantiated or been created. If we zoom in Rhino, and then we left click and drag over this geometry, we'll quickly notice that we can't actually edit or click or interact with this geometry in Rhino. The other thing we see here is a red grid that is drawn out around this geometry. So we see our sphere, we can't click it or edit it, it's red, and then we also see this grid. If we left click on the component inside of Grasshopper, so I'm left clicking on that sphere component, now we see that grid and the sphere are green, but we still can't click it in Rhino. This is because what we've done is created a geometry within the virtual environment of Grasshopper. So all we're seeing is a kind of preview of that virtual environment that exists in Grasshopper. So that's why we can't edit it. It doesn't actually exist yet inside of the Rhino environment. It just exists inside of the Grasshopper one. When we select the component, it turns green to let us know that we're previewing these currently selected component inside of Grasshopper. When we click off of that component, it goes back to red. So anything that is light gray previewed as a component will show up inside of our Rhino interface, and if it's not selected, it will be red by default, and if it is selected, it will be green. Just like in Rhino, to control the construction of this geometry, so in this case a sphere, we need to give certain input parameters or input information to this geometry constructor. So just like when we typed sphere and then we needed to add the point location and then the radius, here we have inputs shown on the left, and if we hover over each one of the letters, we can hover over first the B, which stands for base, and this is requesting a base plane. You can see that next to the word base is actually an icon, which tells us a little bit more about what is required as an input to this node. We can also see at the bottom that one locally defined value already exists as an input, which is the world XY plane. So this is why, by default, our sphere is constructed at the origin of our XY plane. So that's why we can see our sphere exists inside of our Rhino environment at the origin point. If we hover over the R, we can see that this input is radius. We also get an icon next to it, which is 0.1 inside of a hexagon. Any icon that has this kind of hexagon surrounding it is going to be an input parameter, which will allow us to reference some data inside of a container, which can be connected to certain input nodes inside of Grasshopper. So when we hover over the R, we see that this is defining the sphere radius, and currently it has one locally defined value of 1. If we want to edit this inside of Grasshopper, one popular way of doing so is by constructing a number slider. A number slider is going to allow us to variably control that input number value into that radius. So this is what makes it parametric, because we parametrically, variably control the input parameter. We can make a number slider either by going to the tab at the top, and we can look through the options. So inside of parameter, we have options for geometry types. So these are going to be input parameters of geometry types. We can go to primitive and we can see that we have input parameters of things like integers, which are whole numbers, numbers, also referred to as floats, or several other data types that we can input. If we go to input, we have a series of Grasshopper native input parameters, and one of those is going to be our number slider. So we could click this, and then we get a plus icon showing on our mouse cursor, and if we left click, we can deposit this component into our canvas. By default, if we hover over this slider, we can see that this is floating point accuracy, just meaning it does contain decimals. It's a numeric slider for single values with a lower limit, a minimum of 0.000 and an upper limit of 1.000. What's important to note here is that this slider, being not just 0 to 1, is 0 to 1 with 3 decimal places of precision, meaning as we slide this slider across, each value all the way down to that 3rd decimal place is going to be adjusted continuously. So if we slide this from 0 to 1 right now, we get 1,000 different values that are going to be input into our sphere once this is plugged in. If we want a different set of options for our number slider, we can just go ahead and delete that component by left clicking and clicking delete. And then to instantiate another number slider, we can double click in our canvas and just type one number. So if we wanted our current number value to be 5, we could type 5 and hit enter. Again, this comes with a default domain, in this case, which is 0 to 10. So no longer is this 0.0 to 10.0, indicating that this is going to be integer values or whole numbers only. So if we slide this down to the left, we get 0, 1, 2, 3, 4, 5, and so on all the way to 10. If I plug this output node, so this kind of end node on this component, into the node for our input radius to the sphere, we'll see that sphere automatically update. And if we hover over the radius, we now see that that value has changed to 10. As I slide the slider, it dynamically adjusts from 0, which means non-existent sphere, to 1 to 2, all the way to 10. So this is going to give us that parametric variable control inside of Grasshopper. And one of the great things about it being a virtual environment is that since everything is connected, nothing is actually baked or created in Rhino, meaning we don't have to delete things every single time we iterate through. So we can just slide freely and get that adapted output geometry without having to go in and clean it up constantly. If we wanted more control over the values of this slider, I'm going to just go ahead and delete this again, and we can double click on the canvas again. And this time we're going to define not just the current value and rely on a default domain, but we're going to structure the minimum, maximum, and our current value. So give the entire range of the domain for this number slider. We do this for a number of reasons, but if you think about a sphere with radius 0, that doesn't make a lot of sense. It's not a sphere at all. Any sphere with radius greater than 0 is totally fine. One way that we may want to constrain this input is by limiting the minimum to be 1 and the maximum to be some number higher than 1, let's say 20. So we can give this input constraint to the number slider by typing 1 and then a less than symbol, the current value that we would like this number slider to be at, which we can start with 4, and then is less than the maximum value of this domain, which we can say is 20. And then when we hit enter, we now have a number slider that starts with a current value of 4, which was that middle value, a minimum of 1, and a maximum of 20. We can left click and drag. This is going to open up this wire. This wire now plugs into the radius, and once we release that wire being plugged into the radius, it will pass that data from the number slider into the radius input, and we see that that value's been changed to 20. We can hover over the S to preview the output or see the data type of the output, which is a hexagon with this kind of distorted plane on the icon. And we can see it says that there's a resulting sphere. At the bottom, we can see additional information telling us that that resulting sphere is actually just an untrimmed surface. If we wanted to see that without just hovering over this information, we can use something called a panel. If we double click in our Grasshopper canvas and type panel, and then hit enter, this is a way that we can both type in information or store information, either text values or numbers, and either pass it into a component as an input parameter, or we can use it to visualize certain output information. So in this case, we'll take the output node from this component and drag it into the input node on the left, always going from left as an input to right as an output, into the panel, and it's telling us that we have an output of an untrimmed surface. If there was some error in this component, not only would we see this battery or component actually show up as either yellow or red, telling us that there's an error or a warning, but we would also see information here possibly saying that no geometry was created at all. Additional input for this component is going to be a base plane. So a base plane can either be defined with a plane parameter, or in this case, really what it's looking for is just that center point. Like when we typed in sphere in the command line, and all it wanted to know was a center point and then the radius, this also is looking for a center point, but it's just calling it a base plane. Really, it's looking for the origin of that base plane. In order to set a point, we could either construct a point in Grasshopper, or we could use parameters from this parameters tab in the upper left. If we click on the geometry tab and then look at this dropdown, we see that it mirrors some of our early introduction to Rhino steps. So we can see that we have geometry types including point. I mentioned briefly the geometry type vector, which is very similar to a point. So it's also going to be defined by X, Y, and Z information. Then we have circles, curves, lines, rectangles, planes, boxes, meshes, and then we have several other uncovered geometries, which we'll get into in future videos. One important thing to note is that Grasshopper calls a polysurface something slightly different, which is a BREP. This stands for Boundary Representation Geometry, but it's essentially going to be the same thing as a polysurface geometry. So just know in your mind that when you're referencing a polysurface inside of Grasshopper, it's going to be called a BREP. Now, if we hover over this point parameter, we can see that the point with that hexagon icon and the point symbol contains a collection of three-dimensional points. So not only can we set one point inside of this, but we can also set multiple. So it's giving us a hint that that is the information it takes in. Right now it says that there's an empty point parameter, and we see that it's orange, meaning that there's no information going into it. If we hover over this balloon or click on it, we can see the error information says floating parameter point failed to collect data. So it's not an error, which would show up red. It's actually just a warning saying that it's not reading any input information, so the component is not actually doing what it's supposed to be doing, which is referencing some point. So these parameters are fantastic for us to be able to reference information that exists inside of Rhino in our Grasshopper interface. So if we go back to Rhino, type point. So I'm going to type point in our command line and then click to add that point inside of Rhino. We need to be able to reference this point into our Grasshopper parameter and then connect this point parameter into the base for our sphere. So first I'm going to left click and drag over my point, and then we need to hover over the point, right click on this point parameter inside of Grasshopper, and we can see that there are some options for setting one point or setting multiple points. So I'm going to just go ahead and select set one point. And with that point selected, it automatically updates this point and now says referenced point. That's because it's referencing the point that exists inside of Rhino. As we move this point around, we can see that this little red X follows the point, because it's referencing the live point from Rhino into our Grasshopper environment. So we're seeing both the actual point in Rhino and the preview from this component in Grasshopper. Now if I click on the output node from this parameter and drag it into the input for our base plane, plane input or center for our sphere updated as the point inside of Rhino. So we can see that that now is updated, so that point is our central point for the sphere. We can still slide the number slider and adjust that radius, but we can also now select our point in Rhino and move it, and in real time we can update the sphere that's being created or previewed in Rhino from Grasshopper. So we can move it in any dimension, and in real time it's going to update our Grasshopper interface. If we want to pass this information once we've made these adjustments into Rhino so that we can actually edit this geometry, we want to bake it from the Grasshopper virtual environment into the Rhino environment. So we can do this by selecting our component that we want to bake. We can right click and then we can select the option for bake. If we click on this, it's going to ask us which layer we want to bake it to. So we can just say the default layer and then additional information, which right now we can just skip, and then we can click OK. We now see that our preview has turned more solid, and if I left click on this geometry inside of Rhino, I can now move it around inside of Rhino. I can scale it, make any edits to it, and delete it. If I want to slide my slider in Grasshopper, once I've deleted that baked geometry, it's no longer, well actually once I've baked that geometry, it's no longer linked to our Grasshopper preview. So if I make an adjustment to the number slider, bake the geometry, hit OK, and then change the number slider, we can see that that new one that I haven't baked yet is still just a preview inside of Grasshopper, whereas that first one now exists inside of Rhino. So if I wanted to bake the second one, I could right click and then select bake again, hit OK, and now I can edit that inside of Rhino. So now if I wanted to do something like perform a Boolean operation, I can select the larger one, then the smaller one, delete the smaller one, and we can see that performed inside of Rhino. But just keep in mind that that has no impact on the information set inside of Grasshopper because we haven't actually referenced this polysurface geometry inside of the Grasshopper environment. If we wanted to bake multiple components, we can do that as well, just by selecting both of these components, right-clicking off of both components and selecting bake. And now if I left-click and drag over, we should be able to see that 2 points and 1 surface are now added to our scene. And if we type in the command line in Rhino, SELL, to select last, that's going to just select the last 1 point and 1 surface that were created inside of Grasshopper. So if I drag those out and then move this sphere, we can see that we had a point inside of that sphere, which was our reference point, but we rebaked it, so we still have that reference point, which is why that preview has not changed. Then we have the point that we actually baked over here, and then we have our baked sphere to its right. I'm going to go ahead and delete those, and now we're going to just step through a couple of different steps, mirroring some of the early exercises in the introduction to Rhino 3D. So to start out like we did in the Rhino 3D introduction videos, we're going to start with the basic geometry, which is just constructing a point. So here we've referenced the point that existed inside of Rhino, but if we wanted to construct a point inside of Grasshopper, we need to double click inside of our Grasshopper canvas and type point. So when we do this, we can just get here the point reference. So if I click on that, we'll see that that's the exact same as our point parameter that we have above. But if we want to actually construct the point inside of Grasshopper, we're going to need to tell Grasshopper that we want to construct it. So when we type, we want to type in construct, and then it's going to give us all of the things that we can construct, including a plane, a mesh, and several other things. we can already see that construct point is actually in this suggested list. But if we keep typing construct point, then we get access to that construct point component. We can then left click on that, and it will add that component to our scene. I can go ahead and left click and drag and delete that top point parameter. So now we have a point, and if we hover over this construct point component, just like our sphere, it comes with default values of 0, 0, and 0 in the x, y, and z. So if you remember, a point is defined by x, y, and z coordinate values, and right now their default values are all 0, and we can see that reference point at the origin there. Just like the sphere took input parameters and we used a number slider, we can do the same thing for this point. And if we want, we could either reference an individual number, or we could also use a number slider to make it variable. So if we double click, we can type 0, because now 0 makes sense for an input to an x, y, or z coordinate value. So 0 is less than 1 is less than 10. Enter, and this gives us a number slider going from 0 to 10 with a current value of 1. If we left click and drag this into our x, we can see that that already updates so that our point now has an x value of 1, but the y and z values are still 0 and 0. If we plug this number slider into y and z, so just left clicking and dragging to draw out those wires, we now have a point with x, y, and z values all of 1. And as we slide these, it's actually going to draw out basically a diagonal line from the origin 0, 0, 0 out to 10, 10, 10. So we can see it moving as we draw that out. If instead we wanted each one to be controlled separately, what we want to do is we want to copy this number slider and have 3 separate number sliders, each one going into its own component. We can copy a slider either by hitting Control-C and Control-V, or clicking the slider, hitting Alt, and then left clicking and dragging down. We can now plug this into Y, and it's going to overwrite any wires plugged into our Y coordinate input. If I do this same thing again, left click, hit Alt, and drag down, and then plug this into Z, we now have 3 unique number sliders, each one going into its own coordinate. So now if I just drag the x-axis up, we can see our point moving along just the x-axis. If I leave that at 6 and we drag the y-axis, we can see that moving along the y-axis. I can do the same thing with the z. And now we've constructed one point. As we went through in Rhino, if we want to define a line, one way of doing this is defining 2 points. So if I double click and then type line, we can see that the first option here given is a line parameter, and this is to reference a line geometry already drawn inside of Rhino. Additionally, we can create a line inside of Grasshopper between 2 points, as it mentions here when we hover over this option. So I'm going to select this, and we can double check what the input and outputs from this component are to get a better understanding of what the component requires in Grasshopper. So we need a starting point of this line, which requires a point parameter, and an endpoint of this line. So we could either construct 2 unique points in Grasshopper, or we could reference 2 points from Rhino. Well, we already have one point here that we've constructed inside of Grasshopper. If we want to make another, we can select all of these components, left click, hit Alt, and drag down, and we now have 2 points that are both the exact same value. So 6, 6, 4, and then we have one at 6, 6, 4. If we plug each one of these, one into the start point A and one into the end point B, then we'll construct a line that has exactly no length. So I can left click on this point, add it to A, left click on the second point and add it to B, and if we hover over line, we can see that it's an invalid line because it has length 0. Now if we adjust any one of these coordinates in either one of these points so that the points are not exactly identical, then we'll be able to actually construct a line with some length. So if I lower this x value, we can see that there's actually now a line previewing between these 2 points. And if we hover over the L output, we see that there's a line with length 6 millimeters. That's a 6 millimeter difference from our x coordinate being 6 units away, 1 being 0 and 1 being 6. So now as we adjust any of these points, we have a live connection to that line being created as well. So not only are we creating the points themselves, but we're creating the future connections to this line. If we didn't want to constantly be copying one component and all of its setup to the next, which is an incredibly inefficient way of doing this, a different way is to use operators or operations, kind of like we did in Rhino. So one way is in Rhino, we could just click to add 2 points. So if I go into our Rhino interface, I can type point, right? And I can click 1 point. I can perform that operation again, click another, type line, and I can draw between those 2 points. Another way of doing this is by typing in point, clicking, and then I can type copy, select this point, click on the point, and click somewhere else in space, hit enter, and now I can draw a line between those 2 points. So inside of Rhino, we use move or copy to provide a translation or transformation of one object to another location. So we can do something similar inside of Grasshopper by taking one object, applying a transformation, and now using those 2 objects in coordination. So if I go ahead and delete this second point, or we'll copy these down so that we can see them in sequence. I'm just left clicking and then dragging those down. And then I delete this second point set here. We now get a yellow battery because it has no endpoint to draw that line. So now what we want between this point and line is, like in Rhino where we typed copy, if we type copy here, we only get options for this copy trim, which is going to be different than what we want. So because they're virtual references inside of Grasshopper, we don't actually need to specify that we're copying versus moving. We can actually just move the geometry and reference the original and the move geometry, meaning we actually do get a copy just by moving. So I'll kind of prove this and maybe it'll make more sense once we do. So if I type move here, we can get access to a component which says translate, move an object along a vector. So this is where vectors are incredibly important. So if I click on that component, it'll create that component in our Grasshopper canvas. And we want to check, like any component that we make, what the input parameters are. So it takes in a base geometry. This is the most general version of input that Grasshopper has, meaning it takes any geometry type, because the move operation can be performed on any type of object inside of Rhino or Grasshopper. Then the second input is a motion translation vector. So by default, it's a vector with component values 0, 0, 10, meaning that it has a length of 0 in the x-axis, 0 in the y-axis, and 10 in the z. So that's a vector moving straight up in the z-axis 10 units. So if we wanted to move a point from one point in space 10 units up, we would want to use this exact vector. If we wanted to move it instead, whatever this set movement that we've placed here is, we would want to first understand what this vector is. So what we need to do is determine what vector would get us from this starting point to this endpoint. We can do this by checking the x dimension. So drawing a line just in the x-axis here. And I'm using my smart track to be able to draw to that intersection. And then we can select that line and type length. And this gives us the length of the line, which is 13.577 millimeters. We can then draw a second line from this endpoint up, and this will give us the y component value of the vector. So if I type in length, that's the y component value of the vector. And we can see that that's flat, so there's going to be no z component of that vector. So we have 2 values that need to be plugged in with a third value of 0. That would give us the vector for this move translation. If we just go ahead and plug in our first point here inside of Grasshopper to our geometry input, And then we go and take a look at where that point actually is. So when I left click on our point component, we can see that previewed here. And then if I left click on our move geometry, we can see that point moved up 10 units in the z-axis. If we wanted to change that vector, then we could double click, type vector. This is going to be a vector parameter, which we could draw out in space and reference into Grasshopper, or we could construct a vector using 2 points. As I mentioned in the first video, a vector is defined similarly to a line, which can be defined by 2 points in space, giving that directional vector, just like a line is defined by 2 points in space. Alternatively, we can define a vector like a point with just x, y, and z component values. So I'm going to select this vector x, y, z, and this is going to be defined just like the point above. So I'm going to select all 3 of these number sliders, hit left click, and then Alt, and drag those down, and plug each one of these into a component value for this vector. So it's going to take a vector component in the x, which is now going to be 6, a vector component in the y, which is 5, and a vector component in the z, which currently is 0, but now it is going to be 6. It now gives us an output of both a vector and the length of that vector. So we don't need the length right now. All we need to add to this move component is the translation vector. So we're going to take the output vector and plug it into that translation. And we can see now that point has moved in space, so it's no longer directly vertically above our initial point. If we plug the output geometry, which it says here is the translated or moved geometry, into our B, then we'll have a point that is moved in space to construct that line. So we basically have one original point and a moved point, which are now feeding into a line to construct that line parametrically. And we can adjust this vector value to move this point in space. So it's very similar to constructing those 2 points, but this is a much nicer setup when we start getting into more complex operations. And this setup will allow us to really utilize the programming functions inside of Grasshopper. For instance, if we wanted to move this one point, and we wanted to move it along an axis several times, so let's say we wanted to take this point and move it in space just along the x-axis 10 different times, each 1 unit more than the last. So I'm going to take this setup, left click, hit Alt, and drag it down. And instead of constructing one vector here, I'm going to delete just the number sliders, because we still want to construct a vector, but we want to construct not just one vector. We want to take this point and first move it 1 unit in the x-axis, and then second, we want to move it 2 units in the x-axis, and then 3 units, and 4, all the way to 10. So we can go ahead for this and just delete our line input. And we can also disable the preview of our first few components so that it's not so messy to look at. And I'm going to delete these geometries that we've drawn inside of Rhino as well. So we can disable the preview of these top components by left-clicking and dragging over them in Grasshopper, right-clicking and selecting Preview Off. Now if we go down to these bottom components, we see our point, and then we see an identical point because we have a 0 length vector plugged into our move component. So to move this additional units in the x-axis, we could make a number slider that goes from 0 to 10, and then we could hit enter, plug this into x, and we can now see if let's say we'll start this point also at the origin. So I'm going to double click on this slider and type 0, enter, double click on the second one, 0, enter, and the third one. So we now have a point at the origin, and our goal is to make 10 unique points that are drawn out along this x-axis. So if we want to do this, Right now we just have a slider plugged into our X component, and as we drag it to 1, we see our point drawn out at 1, 2, 3, 4, all the way to 10. So it's stepping through the length which we're moving. It's not depositing a point at each of those values. So as we step through here, it's not creating a unique point at every single one of these values. It's just creating a point with whatever that one particular value is. So if we wanted to create multiple values as an input to this vector, so multiple vectors, the first being a move from 0 to 1, the second being a move from 0 to 2, and then from 0 to 3, and so on, what we want here is what's called a range. If we double click and type range, and then click on that range component and hover over it, it's going to say this creates a range of numbers. So the input to this range is going to be a domain, which is the minimum and maximum value, and then also the number of steps that we want in this range. So we've said that we want our range to be from 0 to 10 units. So our domain right now is 0 to 1. So we'll have to construct a domain by typing construct domain and then hit enter. This domain is going to take a start value and an end value. So we can plug in that output into our domain. We know that that's what that range takes. And then we can double click and make a panel, since we know that we only need one number here. And I'm gonna just scale this panel down, double click and type 0. And then plug in this 0 to A. Copy this by left clicking and then dragging, double clicking and typing 10, hitting OK, and plugging that into B. So we can see that that creates a domain of 0 to 10. We plug that into our domain input for the range. And if we just leave these steps at 10 and hover over the R, we can see this gives us an output set of numbers, or a list of numbers, that goes from 0 all the way to 10 and contains 11 values. If we wanted to change the number of steps that we have here, so instead of going from 0 to 10 with 11 values, if we wanted this to be 1 to 10, then we could change the number of steps here to 9. That's going to make incredibly complex numbers here. So we would need to change our input minimum or start for that domain to 1. So 9 steps, 1 to 10, which is going to give us 10 values, including 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. If we added 0 to that, that's what gives us the 11th value. So alternatively, we could go from 0 to 9 by changing this domain to start at 0 and end at 9. And this is something common in programming where we always start at 0. If we want to move 10 times, then we'll move from 0 to 9 rather than from 0 to 10, which gives us 11 values. So now if we hover over the R, we see that we're creating 10 values moving from 0 to 9. So now we can plug the output of all of these range values. So all of these are going to be plugged into our X value. So if we left click and drag and then drop that onto the X, we can see not just one point being created, but if we actually click on this move component and then hover over its output, it's constructing 10 moved geometries, meaning it's running this operation 10 times with each one of these different vector values, first being a 0 length vector, and then a 1 length vector, 2 length vector, and so on. And if we wanted to bake that component, we could right click, select bake, click into Rhino and type SELL, and that's going to bake all of those values, all of those points rather, as geometry inside of Rhino. Now this is significant because, as we know, a line is composed of 2 points. However, a polyline is composed of a list of points. So if we wanted to construct a polyline inside of Grasshopper, we need a list of points, which is going to be the output here. So 10 locally defined values, which is a list of 10 points. So if I left click and drag and then copy these components down, we currently have a list of 10 points here. And if we wanted to construct a polyline from these points, we would double click on the canvas, type polyline, go to the polyline component here, and left click. And now we can see this creates a polyline connecting a number of points. And if we go to the inputs, we can see that the first input is the vertices, so the vertex points, which we have here from the move component. So we can go ahead and left click and drag that into our vertex input. And then we have a toggle for whether or not it's closed. So this is just going to connect the endpoint to the beginning point, which we don't want to do currently. So this is constructing a polyline, and if we zoom in here, we can see that it's drawn out from 0 all the way to the end at that 9th unit there, so the 10th point at that 9th unit. And we're still making each one of those points. And if we were to plug in our range, not just to the X, but also to the Y, we no longer get that polyline drawn across just the X-axis. And in fact, the only thing that we're visualizing here is from the previous step. So if we just go ahead and left click and drag across those, right click and turn the preview off, we see that we're actually making a diagonal line here in space by first moving those points and creating an array or list of these points, and then using those points as inputs for the polyline. If we were to make a different range as input to the Y, then we wouldn't have a directly proportional diagonal line. So if we wanted to select these range components, copy them down, and then change the values here. So let's say instead of 0 to 9, we want to do 0 to 19. And then we want to check this range output, which right now is giving us a lot of decimal places here. So we don't want these decimal values. So we're going to try and adjust the number of steps to match. So 19 steps here is going to give us 20 output values. So what we want instead is not 0 to 19, stepping by 1, but we actually want 0 to 19, stepping by 2, because we still only want those 9 values. So I'm going to change this back to 9 so that we only output 10 values, and we're going to adjust the domain accordingly to make sure that we only have those whole numbers. So if I change that from 0 to 19 to 0 to 18, and then we leave those steps at 9, then we still get 10 values, which are going to range from 0 to 18. Now if I plug this output into our Y input, we get a much steeper diagonal. If I had instead used that input of 19 here, and then adjusted these steps also to be 19, we now get a much stranger set of points for this polyline. And the reason why is because we have 10 values going into the X and 20 values going into the Y. So if we make a panel here, and then we take a look at these vectors that are then being sent into the move component, we'll see that the first 10 values are maybe what we would expect, where we have a 0, 0, 0 vector, and then a 1, 1, 0. And all of those are paired until we get to the 10th one, where we no longer have additional values from the X. So it's just going to repeat that last value in the X. So we get a value of 9, and then we still get a value of 9, all the way down to that number 19 index. So the last indexed item in this list. But our Y value continues to step up. So that's why we see this sharp bend here as it goes into the move. And then if we look at this polyline, we can see that 20 values are going in. So all of these 20 vector values have gone into the move. making 20 unique points, and all of those are being sent into the polyline to construct a polyline. So if we know that we want to increment these together, then we just want to make sure that these steps are the same value in each of these ranges. So I'm going to change this back down to 9, and then change this value to 18 so that we can stay with whole number values here. And now we can see that it goes from 0, 0, 0 to 1, 2, 0, 2, 4, 0, 3, 6, 0. So you may notice this as we're taking a look at these number values, that the y could also be described as just 2 times the x. So if you're already thinking this, you're in the kind of right zone here, which is that to think programmatically, we will always want to try and limit the duplicative components, so the duplicated components, because this gives us a chance for error and is unnecessarily time consuming. So if we know that we want the y value to just be 2 times the x value, then we don't need these components at all. So I'm going to go ahead and copy all of these down, hide all of those components, so disable the preview. And what we're going to do is delete this range, and instead of duplicating those range components, we're just going to make a multiplication component, and this is going to multiply all of the values in this range, so 0 to 9. That's going to go into the A as a number input into the A, and then the second value will take a number input into the B. So we're going to give this, we're going to copy one of these panels and give this a value of 2, so that each one of these inputs, so 0, 1, 2, 3, 4, get paired up with 2, and it's going to multiply each one by 2 to give us an output of 0, 2, 4, 6, 8, 10, 12, and so on. So if we plug this into our y, and then take a look at both of these panels, we can see that they're actually exactly the same. But we've limited it from all of these components to just 2 additional components. And instead of detaching these 2 range operations, we've actually connected them. So now all we have to do is edit this one range, and it's always going to produce y values that are 2 times the x. So we can ensure that that slope value is always the same no matter what adjustments we make to the origin point. So if we change this, we can move it, and that's all linked. And if we wanted to update the range as well, by doubling, let's say, the x value, that slope is still going to be consistent. To take full advantage of Grasshopper and its parametric operations, we have other types of input parameters that can not just change with a kind of multiplication action or multiplication operator, but we can do it more complexly by feeding the values of this range, so 0 through 9, into an equation, and use that equation to adjust those number values, and then input that instead into y. So let's say we wanted to map a parabolic equation as this polyline, or map this polyline to a parabolic formula. We could do that using what's called a graph mapper. So I'm going to just left click, copy these down, disable the preview for those top components, and now instead of multiplication here, I'm going to double click in space and type graph mapper. And that's that second option there that pops up when you type graph, so graph mapper, and it gives us this blank box at first. So what this is just a visualization of the graph type that we're going to use to feed in x values from whatever the input is. So the input is x and the output is y. So it's a 2D graph where this component does the calculation for us. So if you think of it like the equation of a line, what we were doing here was manually making the equation y equals mx plus b, where m is 2, right? M, the slope, is 2. So for every x value, the y-intercept currently is 0, right? That being the origin, the y-intercept. The x value is a range from 0 all the way to 9 in this case. And we know that the y value is going to be 2 times that. So the slope then, m, is 2. So we can do that, but we can also do that with this graph mapper using much more complex equation. We can get started by right-clicking, going to graph types, and if we just selected linear, we see that we have a 0 to 1 range in one axis and a 0 to 1 range in the other. And then we see a line drawn out where we can control the slope as well as the y-intercept of this graph. So we can see here that as we move this left point all the way down, we can get as close as we want to a y-intercept of 0. We can change this right point and then move this left point again so that we get a y-intercept still of 0, but a much steeper slope. And if we move this left point again and then drag this down, we can now still have a y-intercept of 0 and a much shallower slope. So if we just use this linear equation to visualize what this graph mapper does, I'm going to delete this multiplication. We're going to plug in our range into the input, and we're going to plug in the output into y. And we see something quite strange going on here. So what we might have expected is that whatever this slope is, we would see some kind of multiplier of this slope value to the x. What's going on is that it's taking an input of x from 0 to 1, but our domain here is set from 0 to 9. So we want our range here to fit within that 0 to 1 range, so 0 to 0.9, and then we can keep our number of steps at 9 so that we still have 10 values being constructed. Now if we zoom in here, we can see our points that are being drawn out from 0 to 0.9, and as we move this graph, we can see that polyline being changed in our scene. So it's mirroring exactly the position of our graph because we now have a domain that's mapped from 0 to 1 through a graph mapper that's taking in values from 0 to 1, and then it's adjusting them by plugging them into this y equals mx plus b linear equation. And then it's giving us output values for the y value. And then it's outputting this vector. So each of these vectors from 0 to 9 are giving us certain values based on this equation, which are plugged into the move. Each one of those points are moved in space, and then the polyline is drawn accordingly. If instead of a linear equation here, we wanted something more interesting, we could change it to a parabolic equation. And we can adjust the parameters of this parabolic equation to quickly map out the parabolic polyline that coordinates with this equation. And we can see the data updating here to the right. If I just highlight these and then copy these components down and then disable the preview here, we can just test out a couple of different graph types. So if we right click, go back to graph types, and then this time select something like Bezier or maybe sine, we can adjust here the frequency of the sine and approximate a sine curve, or we can draw it out, adjust the amplitude of the sine curve, increase the frequency, but you can see we have far too few numbers, so far too few points to approximate that sine curve. So all we need to do here is just change the number of steps that we have in the range. So if we right click, go to set integer, or change the number value here, we can make a panel, double click, type, let's do 40 to start, hit enter, and we can now plug this number into our steps, and it's much closer to approximating that sine curve. And you can see this update as we make the adjustments to our sine curve. If we don't want a polyline, but instead we want a smooth and continuous way of representing this curve, then what we can do is copy these components again, disable the preview on these previous ones, delete this polyline, And what we're going to want, just like in our Rhino introduction video, is a curve. Now, we can just type curve, and it's going to give us that input curve parameter. But what we want here is actually a NURBS curve. So if we select NURBS curve, then like our intro to curves from the Rhino video, if we plug in all of these polyline vertices into our NURBS curve, just to prove this, I guess I'll also make a polyline component again. So we'll keep this input as the input to our polyline. We can hide these previous points as well. So we'll turn those points off. And then I'm going to plug in this set of points to the vertices input to our NURBS curve. And then the additional inputs are going to be the degree, just like it was in Rhino. And then we have a question of whether or not it's periodic, which we can leave false. So degree is going to be by default 3, which is fine. We did the proof of that in the first video. Now if we plug in this G into V, it's a bit difficult to tell just because we have such high resolution points there. But if we lower the number of points on this panel, as we get lower numbers, we can see that separation of the NURBS curve based on those tangential divisions that we proved in the first video. So we have the polyline, which is degree 1, and then we have the NURBS here at degree 3. Now if I copy this component up and then change the input value, so I'm going to copy one of these panels and then make this a degree 2 input. So we have a polyline, which is degree 1. Then we have a NURBS curve drawn at degree 2. And if I copy this down here, we have a NURBS curve that is degree 3. So we can see polyline, first degree, and then third degree. So you can see right there the kind of parametric adjustment. And as we move this, we can see how that changes the differences between each of these curve types. If we wanted instead for a curve to be drawn exactly through the points and not using those points as a control point, then what we can do is go ahead and copy these components again. And I'm going to delete all of those and then use an interpolate curve, which ensures that the curve is drawn exactly through the points that we are feeding in as an input. So I'll go ahead and make sure that these previews are off, and then plug in on these bottom components are all of our points into the vertices input for the interpolated curve. We can leave it degree 3 and periodic false, and the knot style is fine by default. And this is going to give us an output curve, the length of that curve, and then the domain of that curve. So we can see it's not quite as clean of a sine-like curve, and that's just going to be because it's actually applying these kind of kinked values in order to draw exactly through the points that we've given it. And as we move these points in space or increase this domain value, we can make adjustments to that output curve. So every adjustment to the inputs or the components to the left of this component all pass through to eventually edit or adjust this final component that we're previewing. Now, one last thing I want to show with these curve creation methods, we're just going to copy all of this down. I'm going to hide that component. So right now we're previewing a very tiny curve that is just from 0 to 1, and that was just because of the default settings for our graph mapper. Now, this is a very easy thing to change, but we just have to understand what the graph mapper is actually doing. So it's limiting the preview here. It's limiting this preview from just 0 to 1, or a domain of 0 to 1. If we want to change this, and instead we want to show a domain of, let's say these values are 0 to 20. So let's give an input domain of 0 to 20. And we want to change this graph so that it looks a little bit closer to what the graph is actually showing. Right now it doesn't look anything like what it's showing, and it's very small there, so it is a little bit wider, going from 0 to 20, but our y values are still incredibly small. That's because it's just mapping all of those values still on a range from 0 to 1 there. So if we want to increase these, what we can do is double click on the graph mapper, and then this is going to give us a range for the x-axis and then the y-axis. So we want our x inputs to be 0 to 20, so 0 to 20 to match our domain input, and we'll do the y also as 0 to 20, and we can hit accept, OK. And now instead of that interp curve, I'm going to change this back to a NURBS curve, which will be degree 3, and then we can also change this back to 40 control points. And now as we make this edit, we have a much larger curve being drawn out in space. Additionally, if we wanted to do this in not just this one axis or in 2D, because we can see it's not actually adjusting in 3D at all, we could plug this also into the Z. Now it's adjusting on that diagonal, and as we move it, it's adjusting in both axes. Well, if we wanted to adjust them separately, we can just copy all of these components down, hide the preview, copy this sinusoidal graph mapper, and then just plug in a different one to our Z component. So now we can see this kind of twisting happening because it's following this bottom curve. So that bottom equation as the inputs to the Z, and we can see the number values changing here on the right. And then it's following this kind of top graph mapper equation for the Y values. So we're getting this kind of twisting geometry. So that's all for the curve creation. And now just quickly, I'm going to go through, like we did in the Rhino introduction exercises, how to move from curves to surfaces and then poly surfaces, and then go through a couple of the operations from that first video. So this is the way that we can construct one curve. If we want to construct multiple curves, as we did in that first introduction video, I can copy these down. I'm going to give a little bit more space since we're changing from curves and points to surfaces. So we'll go from this curve, and this time we'll use extrude to go from that curve, extrude that curve to make a surface. So this is going to take an input base curve or profile and then a direction. So that direction we can see is a vector input. So let's just move this. We can move this in the Y. So I'm going to double click and type vector x, y, z. And we're going to give this Y a value of 1. We can use either a number slider, or we can make a panel or copy one of these panels. So maybe we just copy one of those panels, give the Y a value of 1, plug it into that D direction for the extrusion, and then plug in our curve as the base curve for that extrusion. Now, if we change this number value to, let's say, 10, we can get that extrusion drawn out even further. If we changed this panel for a number slider from 0 or let's say 1 to 30, plug that back into Y, now we have parametric control of that extrusion method. So we're constructing that extrusion surface with this parametric control. If we wanted, instead of just extruding, to have two different curves controlling that surface geometry, we would want to use lofting. So I'm disabling the preview there, deleting this extrusion, and then I'm going to double click and type loft. So Loft takes an input set of section curves and then options, which right now we can just leave default, and then it will give us resulting lofted surfaces. So all this means is that we want multiple curves being fed into this curve input. So we don't need this vector information anymore, but instead we need to double these curves that are going into the loft. So just like we did all the way at the top with our point, one way that we could do this is we could select all of these components, drag them all down, and now we could plug one of these curves, so left click and drag to plug that into our loft, but we need two sets of curves at least to make this loft. So what we can do is edit this curve so that it's not just the exact same curve. So we'll move it along the y-axis, and then we'll change it some. So I'm going to just change it on 2 axes here, so they're slightly different. And if I now want to plug this curve in as well, if I just left clicked and dragged, we would replace the first one. So what we want to do is left click, hit shift, and then drag it into that node. And now it's going to allow us to plug in both. So what it's doing is it's combining the data and it's now passing in 2 curves as inputs to this loft component. So we get those 2 curves passed in, and now we can edit the profiles as we want. And it's still going to be performing that loft operation. So you can see that kind of parametrically lofting these 2 curves that we're feeding in. Alternatively, you could perform just a move or some operation to transform or translate one curve and then plug both of those in like we did for the point at the beginning. If we select all of these, copy them down, just like we did in Rhino, after Loft, we went through Sweep, which took in, at least for Sweep 1, took in 1 rail profile and then 1 sectional profile. So we have 2 curves here, but right now they're not starting at the same origin, which for Sweep is not going to create a clean sweep. So we want to use this first geometry as our rail curve, and we can go ahead and delete this loft component. And we actually want these starting points to be exactly the same. So 0 for both. And we can now see, okay, that second graph just had gotten lifted up. So now they're exactly even 0, 0, 0 for the starting point of both. So right now on this second one, we're still iterating through or stepping in the x-axis. So what we might want to do instead is step evenly in the z-axis so that we're moving that rail curve up instead of across the x-axis. So to disconnect all of these wires, we can just hit Control, left click and drag to wherever these nodes are plugged into. So Control, left click and drag from the input all the way back to wherever they're plugged into. And now what we're going to do is we're going to plug in our range into the Z, and that's going to just give us a vertical line there, which is great. And then we're going to use these 2 other graphs to control the X and then the Y. And I'm going to make these a little bit less drastic here. So that we have a little bit less movement in our sectional curve, but a little bit more in our rail curve, so that should be okay. We can also adjust the length here by changing the domain, so we can change this domain to 0 to 10. And you can see it just chopped it in half, so these graphs stayed on a domain from 0 to 20. That's okay, we can just use that. If we cared about it matching exactly what we're previewing, then we could go ahead and adjust these as well from 0 to 10. But now what we want to do is use both of these as input to a sweep component. So I'm going to double click and type sweep. We can use sweep 1. We have our rail up at the top. So that's going to go into our rail curve input. We can left click and drag that down. And then we have our sections. So we can left click and drag our second curve into our sections. And then the only other option is miter, which gives us a couple of options for how these surfaces might join. So right now we can just say trim, that's the default, that's perfectly fine. And now we get an output of an untrimmed surface, which we can see there. Now it does look like it's a little bit messy there as it's trying to sweep across. So that's not going to be the cleanest sweep when we go in to kind of rebuild that. If we wanted to bake that to get a better view, we can select that component, right click, select bake, and we can really see how messy that intersection is. So there's a couple ways that we can fix that. We could just make either the rail curve or the section curve slightly less dramatic, I guess. With less of that kind of twisting happening. Alternatively, what we could do is we could make another one of these curves in order to just use sweep 2 to get better control over that. So I'm going to just copy this whole setup for sweep 1, disable the preview on those components, and then instead of sweep 1, we're going to be using sweep 2. But what we want to do is make 2 of these rail curves, one at that origin point, which is going to match our section curve here. I'm going to move these components for our section curve down, and we're going to copy all of these components to make a second rail curve. Now these are the exact same rail curve, but what we want is this second rail curve to actually align with the end point of our section curve. So in order to do that, we need this input point parameter going into our move. We need that point that's being moved to actually equal the end point of this section curve down here. In order to get that, we can double click, type endpoint. It's actually end points inside of Grasshopper, so we can select on that. It takes an input curve, so we can give it that section curve, and it gives us a starting point and an ending point. So we need that ending point to actually get fed into this second rail. So if we click on that end, drag that node all the way up to replace our origin point, and then go ahead and just delete that component. You now have 2 rail curves with a section curve between them. So now if we double click and type sweep 2, this is going to take 2 rails, so that's our top 2 rails here. So we'll left click and drag the first one into the first, and then the second into the second. And now it's going to ask us for our section curve, which is this bottom section curve. And that's a lot cleaner geometry than our previous sweep 1. So by controlling both the top and bottom, we get a lot cleaner sweeping geometry where it avoids that kind of kinking or self-intersection. And we still have the flexibility to make adjustments to this geometry as well. So we can adjust this sweep geometry, and we can change the frequency on the top and bottom. And if we wanted to bake that, we could just select the component, right click off of the component, and bake. Interestingly, since we're building these actually from this data input, if we click on the geometry and then minimize the Grasshopper window just for a moment, and then go to details, we should be able to see that actually the density from these points, so 41 points, 41, so if we look at each of these geometry components, we're constructing 41 points on each of these curves. So when we select that surface and then go to details in the properties, we can see that the count actually equals 41. The density shown here as the ISO curves. So we're actually seeing the density of the surface being impacted by the number of points that we're using to construct the curve there, which is just a kind of interesting side effect. When you start learning more about the programming, you can understand how each of these geometries are defined and how their properties are set, because it's all defined by code in the background, whether we know it or not. So as we learn more about this, we'll see several more of those connections. To finish out, we can just go back to Grasshopper by going down to this small bar at the bottom left, and we can click to click back in and open up our Grasshopper window. So when we want to go in and save this file so that we can come back to this file for later reference, what we're going to do is go to File, and then we can select Save Document and save that to our local hard drive. That's all for this introduction video to the Grasshopper interface and some of its geometry types, and how to start thinking basically about programming logics. In the next video, we're going to be going through a couple of exercises within Grasshopper, just demonstrating a couple other ways of working inside of the software.